People. Hi, Ben. How are you, man?
Good. It's good to see you, Bill. It's
Yep,
hard to
yep. We
believe another week's gone by. Things just move so fast right now.
It was a fast week. Yeah, yep. And we just went. I can even see it on YouTube. That's always a good sign.
That is indeed.
So, so we were going to. We got to talking in our Discord channel, which you can also find at Coriolis-effect.com. You can find the Discord invite. We started talking about power supplies. I can't remember if we talked about power supplies a little bit in the last show, but today we're going to talk about a few, I'm thinking.
We started to, at the very end, I think last week, we sort of finished off because someone had a question about current limiting, I think, and what's the kind of reasoning. So
Right.
there's a huge variety of power supply types and topologies and everything, and we like to talk about bench and lab power supplies because that's what we tend to use every day.
Right.
And so you
Right.
want adjustable voltage, adjustable current limit, obviously to stop the magic black smoke or things blowing up in your face. But it came up, someone had mentioned using ATX power supplies.
Right. Right.
So just for people, because I feel like ATX power supplies have kind of gone the way of the dinosaur by now, pretty much. Because I just realized most of the computers I know people are using now are laptops. And so for those that don't know, an ATX power supply it is a standard form factor power supply for a computer motherboard. And these are called ATX because they're part of the AT extended industrial standard form factor, which derived from IBM PCs. So IBM came out with the IBM PC in 1981. 1982 or 3, they came out with the IBM PC AT, which stood for Advanced Technology, and that was a 286 processor. And with those came IBM designed a standard sort of pin out and way of connecting the switching power supply. And
Right.
here's an interesting anecdote that I learned when I was in college when we did a whole class on computer troubleshooting and servicing. So I did college level first, and then later on went to university to get my bachelor's. But when I was in college, we had this class about computer technology, and it was all about servicing desktop computers. And we actually went through the whole AT power supply.
Oh, wow.
Because that was arguably one of the first, if not the first, switching power supply, switch mode power supply used in a personal computer. Before that, they were all like big linear bricks. Like the Commodore power supply
Oh,
had a big heavy
or,
transformer in it. Yeah, that's a linear
yeah.
power supply. You can tell because it's heavy, right?
Yes,
So
you
that's a
can
lot.
tell because I just got a hernia.
There's a lot to discuss about. There's a lot about power supplies, and a lot of engineers specialize just in that. I've got a friend, Chris, whose whole career, until he became an applications engineer for an EDA company, um, he had a whole career in just power electronics. There's a lot there.
Right.
So
Right.
that's kind of what we're getting at today. And we know some of the viewers and people who join us are asking, like, what's a good place to begin and what should you aim for? So you got some cool schematics and stuff showing up there. What do you want to start there?
Well, if it's okay, I was going to show what an old-fashioned bench supply, which I took a picture of rather than drag it down. And this is what I was thinking of last week when you talked about current limiting. This is just something I got out of Future Electronics back when they had stores everywhere. So it's almost a nameless brand, but what it has that's useful is it's got a dedicated 5-volt supply, which is real handy. You can see it here on the right.
Yep.
And then it's got a tracking supply so that you can either make it as two independent supplies or a plus or minus 5 or plus or minus 15. So with this, I can do analog and digital, and I have nice analog meters. I actually kind of like analog meters. And you see the knobs for voltage and current. I can adjust the voltage, but then adjust the amount of current that it will supply before it trips, before it goes into current limiting mode. And that little red LED will come on that says CC when I get into that mode.
That is a really nice supply, by the way, because
it's
I
cheap
see it,
too.
it goes up to 30 volts, probably even
Right.
32. So you need that if you, for example, if you want to design audio power amplifiers for driving speakers, you need at least a plus and minus 30 volt. So to have the series tracking, two 30 volt supplies co-regulated, so you get exactly the same positive and negative supply rails referenced to ground. They track. They have. Question? Will it current limit those separately when they're in tracking mode, or will it do it together? I assume it would do it together.
When they're in tracking mode, I have a knob for current for each, for the high and for the low.
Okay. Okay, and I guess the red LEDs tell you when you've got a load that's invoking the continuous current mode. So that's current limit. And then other than that, the green LED would be on, showing its regulated voltage.
Constant, right.
Yeah.
And what I've done before is actually start with it in current limit mode and then come up slowly until, you know, if I think a circuit should pull 200 milliamps, but it might have a shorted cap or something, and I don't want to find the shorted cap by an explosion.
No.
I'll start low and come up, and if I go to 300 mils and it's still in current limit mode, I'm like, whoa, something's not right.
Yeah.
You know?
Yeah.
So it's really useful for that.
That's the lab procedure. You always plug a shorting lead into them. You set the current maximum first.
Right.
Then you unplug it, set the voltage. Then you turn it off or disconnect it. There should be a master disconnect, but you turn the power off, hook it up to your test circuit, power it on, and then if you see the current limits invoked, there's a problem. You turn it off immediately. So this is the advantage of a proper lab power supply, is it gives you that procedure to prevent blowing stuff up in your face. And you need that. But they're expensive.
Wear your safety goggles. Yeah. Now
they're a lot cheaper than they used to be, though, of course. But what would be kind of a decent price range? And you can. The other thing I love about power supplies for labs is they don't change. They're all the same technology over time. There's really nothing new. So you could buy one that's 30 years old, and as long as it's in good working condition, it could last you another 20 years. It'll be useful no matter what. It's not like you have to get the latest, most high-speed CPU.
It's a power supply.
It's a power supply. Yeah.
Right. Now, I went through about 3. I kept trying to buy these overseas ones that are, you may have seen them. They're about this big.
That's like the one I have.
I bought 3 of them, and none of them worked. And so I just stopped trying to buy that particular look and feel. And I was getting them off eBay. You know, so just because we say power supplies are rugged and whatnot, doesn't mean you'll get a working one off eBay. Just disclosure.
I would even venture to say, for anyone who's getting into electronics, one of the first things you should do is design and build your own.
There you go.
There's plenty of reference designs. All the data sheets for the linear regulators show how you can add current capacity to them by putting a second pass transistor on them that's got more current handling if you want higher current. They also show how they do current limiting with the linear regulator. There's Dave Jones. He kind of walks through a whole power supply design that he did as well, which is, he's already got all the traffic, so it's not like I need to promote him. But I've got to be honest, he did the most thorough, best job on discussing power supplies. For designing and building your own and how it all works that I've seen anywhere.
It's a good chance to learn about heat too. My very first Hackaday video was about heat, of all things. It was a complicated topic. It's a simple topic I made overly complicated in that first video, but it's great to learn. You can learn how to manage heat with just addition and subtraction, a little multiplication.
Yep.
So now there's one problem with this power supply for doing FPGA designs, for example. and that is, I wouldn't trust this thing to give me 1.2 volts solid, or even 3.3 or 2.5. What happens if you hit the knob, right?
Oh yeah.
I mean, because these are very coarse adjustments.
Control. Yeah, that's right.
Right, right. So here's what I have on the bench for doing like FPGA-ish things. Let me pull it over here.
Yep.
And what that is, that's a Tektronix chassis called a TM5003. And then I've got 2 plug-in modules, and you see I got one dialed up for 1.8 volts. That one, I'm not worried about hitting the knob on that one. It's got a coarse and a fine adjustment. So this is how I envisioned power supply, 3 volts, 1.8. The reality is I would probably stick more 5004s in here and get rid of the triple supply there if I wanted to do 1.8, 1.2, 1.8, 2.5 all at the same time.
That is really nice instrument right there.
It is. It's in the TM5003 chassis is a real solid Tektronix chassis. Again, this is all pieced together off eBay. So you had asked how to build your own bench sometime. You know, eBay, your mileage may vary, but sometimes some of the old workhorse equipment, still old workhorse equipment.
It just doesn't, yeah, it's workhorse. It doesn't die as long as it hasn't been abused.
Yep.
Yep.
So,
yep.
So
Good
that's,
stuff.
which brings us to what I made myself. Now, do I really use a power supply for 1 volt, 1.2 volt, 2.5, and 3.3? No, because usually on my circuit, I've built those power supplies in. So more often than not, I'm back to using a 5 volt supply as a USB connector, occasionally a 3.3, but I'll break down all the voltages myself on the device under test.
Yeah,
but
so you'll have all the so it's called point of load. So you have point of load regulation on pretty much every digital board where you need lower voltages. FPGAs is a good example because you almost always want a 1.2 or 1.8 volt
for the core
supply for the core because it reduces power consumption pretty considerably.
Right. Yeah. Right. So what I did though prior to that, I actually did this playing around. I created a multi-voltage supply. Let me zoom this sucker in and get these guys out of the way. And what I've got here is an LTM 4603 here. That's this guy right here. He's good for 6 to 8 amps. He's a switching supply, and I use jumpers to pre-program him from 1.2 to 5 volts. And then I have 3 other supplies that you can set to 1.8, 2.5, 3.3, all on one board. And if I pull the schematic down.
Now those are all switching supplies. I see the inductors in the circuit there, right?
Yes, they're all switching supplies. Yeah.
All of those are buck regulators.
Right.
So
right.
they're much more efficient than a linear. And that's
I could never get this much current. Yeah, I could never get this much current on a board like this if they were linears. So what I did on the input here, though, I'll just use the schematic rather than try and pick my way through all these other. Oh, there it is. Yep. Yeah, let me pull him down.
That's a PDF of it. Yeah.
Yeah, so what I did here on the top left is I actually made it so I can take AC or reverse polarity, so I built a full-wave bridge rectifier. So you can literally give this thing garbage in theory. I mean, it shouldn't be a noise source. Let me back up and say that. But I can give this thing a variety of power supplies I had laying around, and it'll turn it into the 12 volt internally or any voltage above your voltage you're trying to make.
Right. That makes sense. Yep.
Yep. And the other thing I did here,
get a little bit of loss in because the full bridge rectifier you have at full load, you probably have 1 volt drop across each of the diodes. So
even though I'm using Schottky diodes, yes, we call it the IR drop, right? Just the plain old drop for being an apparent resistor in the circuit. So And the other thing you and I were just talking about before this is in addition to being able to hardwire with these screw terminals,
Yeah.
is I have through-hole banana plugs, so I can plug in my banana jacks without using a lot of space on the
I
board.
like that. Yeah.
Whoops.
Have you hosted the design for this anywhere? Have you put it up on GitHub so anyone watching could go build their own, or what's the deal
No,
there?
I haven't, and that's probably not a bad. This would be probably not a bad circuit to make available. I just have to check to see if those chips I'm using. Well, again, I'm using the LT 1959 for the small ones, and the LTM 4603 for the big one. I have to make sure they're not obsolete already. You know, at 3 years sometimes seems to be a lifetime these days in some of the chips out there.
Yeah, that's right. That's the hard thing. But that's something I love about the typical LDOs, the low dropouts, linear regulators on the market. They've kind of evolved, but they're just so pervasive, and there's so many drop-in replacements. So again, we were talking about the 1117. This is like the replacement for the LM317, which was the earlier variant, and not so low dropout, as Matt Berger and one of my friends said the other day to me, the not so low dropout regulators. But the 1117 was an improvement on that, and basically same packages, same pinouts, almost pretty much a drop-in replacement. But first of all, for those who don't know, Bill, tell us, what does low dropout mean?
Well, in the old days, you needed 3 volts more than if you wanted to make 5 volts. You needed 3 volts to be dropped in the regulator due to the design of the regulator, which meant you had to give it 8 volts. So you needed 8 volts to make 5 volts. Well, wait a minute, 3 volt drop at 1 amp is 3 watts.
Yeah, so your regulator's getting hot, you need a big heat sink, you need this, right? This is exactly what you're talking about. So this is my generic op-amp and digital power supply circuit that uses LM317 and 337 for the negative rail. And they need 3 volts over the output, which I've set to 15 on this one. So this is a plus and minus 15 volt power supply, but I have to put these huge heat sinks on those because of that dropout voltage. And it's called dropout voltage because if you go below 3 volts above your regulation voltage, the thing drops out of regulation and stops regulating.
Right. So now, you know, what's interesting is I've already deleted off, but my one bench supply that had the continuously variable voltage, my digital supply is not continuously variable. You punch in the voltage you want. Sounds good, but sometimes, yeah. But with the continuously variable one, somebody sent me a circuit that had hum in it. It was a combination. It was actually an old Motorola 6805, whatever the. But it turns out that they had a 6 volt lead acid battery. Oh, this is actually for laser tag, is for the vest and everything you wore.
Oh.
And it had a small 6 volt laser or 6 volt lead acid battery, and they needed to make 5 volts out of it. So they had an LDO. Well, somewhere along the line, if they lost the specification that they needed a low ESR capacitor. The price you pay for LDO regulators sometimes is you got to have a better capacitor. You need to put some money into your capacitor so its effective series resistance is less.
Right.
And the guy was doing something interesting. He was buying the most expensive capacitor he could get without realizing that generally that meant a lower ESR, but in this one case, he'd gotten into a batch of higher ESR. And when I put it on my bench at like 7 volts, there was no whine in the audio. It was fine. So I got with him, I said, it's not doing it. He's like, well, and I said, tell me more. And it turns out it was based on 6 volts. So I slowly lowered the voltage, and around 6 volts, I hear in the audio. And as I turned the knob, it went, and I'm like, okay, I'm near the problem. All right, it's the voltage input. And sure enough, I traced it and found this cap, put in a different cap, and the whine went away. But I found that because I had a voltage control knob on my power supply. So, that's why I still have. And I went to find my linear supply the other day, to take a picture of it. And I'm like, I can't find it. I even emailed a friend of mine. Did I give you my old linear supply? And he said, well, it turns out it's on my bench. I just didn't see it up there in the top left corner because all my other supplies are in the top right. So I'm being an old man and I can't even find my own supply on the bench.
You just got too many test instruments and stuff there, Bill. You gotta. No, I'm kidding. You can't.
Yeah, the supply's the only redundant one up there. I'll give it that. But yeah, I'm waiting for that bench to fall on me and kill me. They just find my legs sticking out from under it like the Wicked Witch of the West,
Yeah, you'll shrivel and curl up. Yeah.
But now show us. You have an ATX supply. Did we talk about? My memory's already between.
It came up. It came up during the week on the Discord because. Quite some time ago, a lot of the time for a lot of the things you design, you don't need super low noise. You just need a source of 5 volts and maybe plus or minus 12. And the computer power supplies, the ATX supplies, which we started out talking about, it's just a convenient source of that. And for a time, everyone had these things piling up around them. As you get a new case for your tower or your gaming machine, you end up with a spare power supply. You need to get a new power supply because you get a new video card. And so what do you do with the old one? It's just sitting around, but they work fine. And so a bunch of people started posting, I'm talking 10, 11 years, 14 years ago now, a bunch of people started getting on Instructables and posting, I converted my old computer power supply into a bench power supply. And they were cutting, drilling holes in the actual ATX case and hardwiring in banana, jacks like these into the ATX case. And I looked at that and thought, you're actually encroaching on safety distances from your primaries, from the offline side of the power supply, which is connected to your wall outlet. It's dangerous. You're not going to have as much safety isolation. All sorts of things can go wrong. So I designed my own breakout board. This was the first version of it, which still sits on my bench to this day, is the most used power supply in my lab, even though I have I have the adjustable voltage, current limited proper lab supplies as well. I use those when I need a low noise and current limited source, but for just breadboarding and getting 5 volts to do something with some digital logic, this is what I use almost all the time.
Okay.
And so I actually did a second revision of that was a lot nicer. The 4049 on it is just used for some soft on-off switching and drives some LEDs in response to the power good signal. So this gives an update of the status. And so this was published in Elector magazine, I want to say in 2012. And I started selling these as a kit, and I sold quite a few of them, hundreds of them. People all around the world wanted them. I still have.
Are you still selling them?
It's possible. I officially have them on a website, and you can order them. But I think the number of ATX supplies in the world has diminished. But I'd be happy just to sell them at cost to anyone who jumps on our Discord. And it just, I don't know what it cost me, but I'll do the numbers, and I've still got a bunch of banana jacks to go with them and everything. But anyone who wants one, just let us know and we'll work it out, because I've got tons of these boards left in my shed. They've been very popular.
The website's jordandsp.com.
Yeah, it's old, out of date, but I need to get onto that. That's on my to-do list this year.
It's like there's too many things these days. Yeah. Technology gives time, but it takes time away.
It does. So one thing I'll mention about this is I spaced these at their kind of standard 3/4 inch, or like there's a a standard spacing for banana jacks that
Okay.
you have if you have a coax or a twin lead, and there's a dual banana jack on the back. It'll plug straight into those, and so each one has its reference ground. The other thing about this was it had these little slots around the edge are for clipping on with alligator clips. So if you don't have banana jack leads, you just got alligator clips, you can clip those onto the board and get it that way. But I always say with anyone using ATX supplies as bench supplies, they can deliver a lot of power. They can deliver on the 5-volt rail. They may be able to deliver 200 or 300 watts, which is what's 300 divided by 5? It's a lot of amps.
60. Yeah.
It's 60 amps. So an ATX power supply, if you short it out, your leads will melt. I'm just telling you now, you'll melt traces on the printed circuit board if you use a printed circuit board like these breakouts. And this is why the one you have there, which I think is from SparkFun, if I'm correct.
It's just some overseas thing, yeah.
Yeah, maybe. They put fuses on it for that reason, because you want to blow a fuse instead of fusing your circuit board trace.
Right, right.
And it's super easy to short things out when you're dealing with experimental stuff on a bench. So you just have to be hyper aware that with an ATX supply, you could have 60 or 100 amps flowing and stuff gets really crazy.
So when I was in I had a basic electronics class in high school, and then I quit and joined the National Guard. And when I came back, they said, "Oh, you must actually be interested in electronics. We'll go ahead and give you a VOTEC class," because they literally said I wasn't academically inclined enough to take electronics in high school. So we had this bench supply built into the bench. I mean, it's truly a bench supply. It's built into the bench. Selenium rectifiers. There's like a little sign somewhere that said, if you smell rotten eggs, leave the room, because selenium will kill you. And then the teacher at the beginning of the year says, "I'm going to show you something, but I don't want you to do it." So we're like, "Go on." And he takes he takes 2 alligator leads, plugs it in the 60 amp supply or whatever it is, and then takes a lead pencil piece of graphite, puts it in an alligator, and he strikes an arc, and pretty soon he's got a small carbon arc, and we actually welded the alligator lead so it wouldn't work any longer. So, you get a supply big enough, you can arc weld it with it, is kind of the moral of the story we took from it. And of course, we waited till we had a substitute teacher, and then we sat there all burning our retinas arc welding with it.
Yeah. We used to get the mechanical pencil graphite rods, the real thin ones. And there were marks in the benches in college in that particular lab where they just melted themselves into the bench top through the melamine into the wood. So
that's cool. And that's how they used to do. If you've ever heard of like Super Troopers, the old stage lights that you work, the big honker things.
Yep.
They're carbon arc. They really are, and they adjust the carbon electrodes, the distance, and you see this column of heat coming off of them. We're throwing away. I don't know what the efficiency is, but I gotta believe they threw away 95% of the power to get 5% light out of those things.
Yeah,
big carbon arc things. So yes,
I'm so glad we have LEDs now.
LEDs.
Yeah, LEDs and that's true. I still think the big stage follow spots. I used to do lighting in the 90s. Professionally, while I was studying electronics in college, I was doing lighting on the weekends to make ends meet. And we used Xenon then. I think we'd still use it now for the most efficient high power source, like car HID headlamps kind of thing.
Right. Now, when I was when I got back to and I rejoined high school after going through basic training and everything. I started doing lights for a local rock group called Primo back in Marion, Indiana, back in the 70s, if you can dig it. And I used thyristors to turn on. I took an organ keyboard, and each one controlled a channel of light, so I could play the lights. And I had my flash pots way off to the side. And the one thing I did that I was proud of, in addition to creating the controller that would safely, turn on and on, and I'm using incandescent lights and I'm wrapping them with gels and stuff, is that I actually took the time to build RFI suppression coils and capacitors into it. So that because I didn't want to get up there and you hear, as they're trying to play their music, I'm playing the hum, right?
Yeah.
So I did a good job. And then if we were in a venue, we would plug, like in a bar, for the smaller things, we'd plug all the audio amplifier gear up in the stage, and then I had a 200-foot cord. I've been known to run it down the hall to the neighbor's control panel, fuse panel, and tap off somebody else's power, just so I wouldn't cause hum and stuff into my own guys' amplifiers.
You're such a considerate lighting guy, Bill.
It makes until you see the fire marshal wasn't crazy about this big power cord, like, streaming out the door of the bar, but
Yeah, but the sound quality and the performance is the
that
most
was all that
important.
mattered. Yeah, yeah, and not setting the place on fire, that was up there also.
Yeah. So
Do you-
you were holding up another power supply before. Tell us a little bit more about that one. We need to come back to the schematic too. We haven't really gotten into that yet, but
Oh, that thing there? Wait, do you mean this big heavy thing? This is a Lambda. I should have given
Yeah.
this to Wes when he was over here about a month ago now, I guess. You can
What's
see
the
the weight
deal
of
with
it.
but what's the deal with that front panel? I can't really see what's on that. It just looks like a bunch of bolts.
It's a bunch of hex head bolts. Let me see if I can. This thing has so much weight to it that it's got a huge steel frame in it just to hold all the transformers and whatnot. But you can see
Wow.
the voltage ratings. They're not huge. Back then, this was supply, like, and it just uses screw terminals.
Right. So that's kind of an industrial linear power supply.
Yeah, it's
So it uses
yeah,
the 60 cycle transformer. That's why it's big and heavy.
yep.
Right. So that's another subject that we need to come around to. But you were getting into this. So I guess your schematic here is a good lead-in for it. Is these are DC to DC regulators, not linear regulators. And
Right.
And you've made them adjustable. So tell us a little bit more about these. These are buck regulators because they drop the voltage.
They
through
drop
an
the
inductor.
voltage. Right. And the main thing that stands out, for me for this is my main regulator here has a 1 megahertz switching frequency. And it's got its efficiencies like 90. It's in the 90s. Hang on, I have that value here actually, which for back when I did this was pretty good.
Yeah, that is
93% efficiency.
at
So,
full load. But at zero load, of course, there's 0% efficiency. But
Yeah.
data sheets only ever tell you the efficiency at full rated load. because
It's
that's where
ideal
it's best.
efficiency.
Yeah.
Yeah. As
Sometimes
soon
they
as
give
I
you
s-
a graph of load versus efficiency too, and you can see the
Right.
sweet spot. Yeah.
and the quality of your inductor matters, things like that. The type of diodes you end up with, because the diode, I don't want to get over my skis here, but I was going to say the diode commutates the charge to the inductor, but I don't
does.
want to try and explain all that. But if your head's in the
Zoom
right
in.
place, you can explain it.
I've studied power electronics. So zoom in to on your schematic. So yeah, that one. So we're looking at U2. That's a integrated switch. And by integrated switch, we mean there's a power transistor that's switching. This is why they're called switching regulators or switch mode. Switch mode was actually a trademark of Motorola, so technically we're not supposed to call them that, but everyone does anyway, right?
Right.
But a switching regulator has a power transistor that is switching to charge up the inductor. So if you look at the top channel there's L1, a 6.8 microhenry inductor. If you apply a DC voltage to an inductor, the other side of the inductor is charging the bulk storage capacitance, that's C32. and C14 and C15 are your decade noise reduction decoupling caps, but the bulk charge is that 150 microfarad C32. Okay, so imagine C32 is sitting at your nominal, let's just imagine the steady state conditions. C32 is at your nominal output voltage of, say, 3.3 volts. It's charged, it's driving a load. The current to provide that voltage to the load and its current is coming through L1, right? And going through the load, returns through ground, and then that D6 diode, which has got its anode to ground, is actually conducting that current back in its loop back into L1. And so that you have this whole current loop. And L1's
Whoop, lost you.
current, am I dropping out?
Okay, you're back. You had just started to say, in that L1.
And that L1, the current starts to drop because it's got a magnetic field. It's stored energy in the form of a magnetic field.
Right.
And inductors, when you apply a fixed voltage, the magnetic field sets up and begins to, the current through it begins to increase linearly as the magnetic field sets up linearly. And then when you take the voltage supply off, the current drops linearly. So the current through that inductor goes up and down like a triangle wave. But usually it drops faster than it's charging because the load is applied. When it's discharging, the load is applied, but there's nothing feeding into it more.
Right, right.
Everyone follow? I don't know.
Yeah,
it's hard to describe this without looking at the waveforms. But then, so what you have inside U2 in the regulator controller, you have a MOSFET or a transistor that's turning on to recharge the current in L1 and bring it up and keep it regulating around the nominal output voltage. And so D6 there is what's called a freewheeling diode, because when the transistor disconnects and the inductor is discharging into the load and the bulk storage cap, the return ground current has to be able to go in a loop. So D6 begins to conduct through L1. So L1 is still dumping its current into C32 and into the load. And then before the voltage drops below the regulation threshold, the switch inside U2 switches on again to bump it up again and keep the voltage from dropping below the regulation set point. And so switching regulators are very, very efficient because the transistor is either fully conducting or fully not conducting.
Right, right.
And so in theory, you can approach 100% efficiency because you're not using a transistor in its linear region where it's behaving like a resistor to drop the voltage for regulation. And so that's what a low dropout linear regulator does, is it turns a transistor partially on to regulate the output. And but there's a very important difference then. A switching regulator has that triangle wave shaped ripple on it as it's turning the inductor on and off and on and off to have it move around the set point output. There's always a ripple current and ripple voltage, and it's usually within a fraction of a percent or within a percent of your set point output voltage, and that's probably totally fine for any kind of digital electronics. But if you have RF or sensitive analog stuff or audio, audio is less of a problem than it used to be, because these switching regulators used to operate down at 20 kilohertz, and they would beat with audio.
You could hear it. Yeah.
And it would create audible noise in your circuit. But like this one, you're looking at switches, some of them switch at a megahertz now or 500 kilohertz. So they're way, way out of order of magnitude away from the audio frequency range. So it may not matter. But sensitive analog, you want to use linear regulators because they have much lower noise, typically. Not always,
Right.
but typically.
Right.
Yeah.
And I still use linear regulators even on FPGA circuits. Sometimes if you just need, a couple mils at 1.2 volts, you can't beat the space that you use in a linear versus getting your inductors and everything that accompany a lot of switching supplies.
Well,
Though
plus
there
it's
are
just
switching
cheaper.
modules.
You have
Yeah.
one cheap device with a decoupling capacitor,
Right.
or you have a more expensive device with an inductor, and inductors are always expensive.
Right.
Always.
They're
And a
expensive to
bunch of
handle,
capacitors
install. Yeah.
and
Yep.
resistors for the feedback loop and all that. I mean, it always costs more to have a switcher,
Right.
but
And
you want the efficiency, right? So
And here's the block diagram of the 1959, the LT 1959. And to what you said, it's either on or off. You can actually see there's a flip-flop circuit that drives the onboard. There's the power switch you were talking about. Sometimes the power switch is something you can put externally with its own heat sink. I like the ones where it's built in, like you said, and this one has one built in. But you can see it's a flip-flop driving it. It's either on or off, or switching between on and off, which is where the word switching supply comes from.
now, here's an interesting point about the way a lot of these work, and this one includes this. It's got that boost pin, and so if you look at Q1, the power switch, that's an NPN bipolar transistor, and to turn an NPN transistor on, or an enhancement mode N-channel MOSFET, you have to pull the gate if it's a MOSFET, or the base if it's a transistor. You have to drive it. You have to drive current into it, which means its voltage is going higher than the emitter pin. But here, the emitter pin is actually, it's acting as a switch. So the emitter pin's voltage, when it's turned on, is going to be close to the input voltage of the whole system, which is your highest voltage in the system is your input. So how do you get the base of the transistor to go even higher than your input voltage to turn the transistor on properly? That's where that boost pin comes in. You have to do what's called bootstrapping. And the bootstrap is where on the output side of that transistor, the emitter, it has a nominal voltage that's kind of, when it's switched on, that voltage is as high as the input voltage. And then that has a capacitor, which when it's low, the capacitor's top end is attached to your input voltage. So it charges up to the input voltage, which might be 15 volts, say. And then when the transistor turns on, that capacitor is pushed up. So this is called a charge pump.
Right.
The other end of that capacitor goes up to the output of the switch, which is 15 volts at that point. So the top of the capacitor is now 30 volts, and it charges another capacitor inside that little driver circuitry block that's inside the chip. It has a small capacitor inside there in the silicon, made in the silicon, with interdigitated conductors, or however it is they do it, on many layers. And that is then charged up to 30 volts, or it probably drains a bit and maybe drops down to 20. But the point is there's enough voltage there in that drive circuit to push the base of the transistor up over the input supply voltage to turn the transistor on. That's all very complicated. And why the heck would we want to do that? Why would we not just use a P-channel device and pull the base down like an inverter?
Well, it's easier to make the N-channel devices first off.
Yeah, so the silicon, it comes down to the silicon process, right?
Right.
They could make P channels, but I think the doping and everything's quite different. So I'm not a chip designer, but
yeah, they're not as efficient as what I remember and things. But I can't really. There'll be people say, no, you can make PNP be near the same as NPN, and you could, but
I've heard that they won't switch on and off fast enough for, like, if you want a power circuit with a power transistor that's switching at 500 kilohertz like this one, it's going to be hard to make a P-channel device.
Right, carrier mobility and whatnot. You're actually using holes instead of electrons to turn things on and off.
Right, and so that's like moving a train versus just one car.
Yeah, yeah,
yeah. So it's hard. So P-channel devices just don't switch fast enough, and sometimes have higher on resistance and things
and more geometry requirements on the board and stuff. So this transistor is almost in an emitter follower configuration as we see here, right? This is a common emitter.
Yeah.
I'm sorry, that's an emitter follower, not
it's an emitter follower. So it's not even there's basically a gain of 1. So it's really just a basic switch.
Right.
And yeah.
Cool.
Yeah. So the other way that can be done, and there are boost. So this is a buck converter. So it's taking your input supply and attaching it to your series inductor in series with the load and parallel output capacitance. Right. And a freewheeling diode keeps the current going. When the switch turns off, the current keeps flowing in the system, and that's a buck. But the other way is you can have a common emitter output stage. So your emitter of your power switch or source, if it's a FET, goes to ground, and you have an inductor from your input power supply to the drain or collector. And when that turns on, it's pulling current into the inductor back through ground from your input. But then when you disconnect your switch, the current has to keep flowing through the inductor somehow, but your switch is disconnected. So where does the current go? It has to go out somewhere. So if it's a true open circuit, the inductor voltage will spike way up.
Way up.
As it tries to keep the current going.
In infinity, if there's no losses whatsoever, right?
In theory, yeah, but your whole circuit's going to have some resistance around it and through the board and things. So it's going to spike, and this is how you make higher voltages from lower voltages. You have a boost. This is called a boost circuit. But what you do, or it's also called a flyback circuit, named after the way TVs used to work. But you have, instead of your freewheeling diode like in a buck, you have an output diode that higher voltage gets pushed through the output diode into your bulk storage and to a load that's at a higher voltage. So, and I had other little boards like, I don't know where I'll put it.
Yeah, I was gonna say, show us some of the things you were, you had a whole handful of boards here a bit ago.
Thinking of, I've lost, but you can buy these off AliExpress, real cheap. There's things like this is a Bluetooth power amp audio device, and this wants 36 volts to get the full output power. 36 is kind of a weird power supply voltage. So you along with that, you get this little module that's a boost regulator that'll take anywhere from 8 to 12 volts input, and you can adjust the output and get your 36 volts on the output. It has a big inductor on it and N-channel output switch to give you the boost. So
that's the other regulator. That's the LTM4603, which is in a bigger case. It's more expensive, but you can see it's also had more stuff added to its drive circuit.
Now that one, instead of using a freewheeling diode, it uses another MOSFET.
MOSFET, right?
And the reason they did, and this is called a synchronous rectifier, because instead of just automatically conducting when the top power switch disconnects, a freewheeling diode just instantaneously starts to conduct to keep the current flowing through the inductor. In this case, it will do that through the body diode of the FET if we don't otherwise drive it, but we can switch on the FET right at that moment. If you time it exactly right, which the control circuit does, it turns that FET on, and it has a lower RDS on body resistance, or channel resistance is lower. And so instead of a 1 volt or 0.6 volt drop across that diode, which is lossy and it gets hot, right? You
Right.
get closer to 0 volts because the channel resistance of that FET is much lower. So, and it's not a PN junction; it's just a channel. So
Right.
that
Right.
synchronous rectifier actually significantly improves efficiency. That'll get you from the 88% efficiency up to the 95.
Right. Right.
Just doing that kind of thing at full load. At partial
Right.
load, of course, everything's less efficient, but yeah.
So the one thing that jumps out at me is they showed the 5.1 Zener there, and I'll say, just to be nitpicky, at 5.1 volts it's not a Zener action, it's an avalanche action. So that's actually an avalanche diode at 5.1. Somewhere around 4.3 to 4.8, it stops being the Zener effect and starts to be an avalanche effect in the diode. But it doesn't matter. We still call them Zeners.
I never knew that. I just learned something brand new from you, Bill. This is why we do this.
Yeah. Yep. So very cool. Did you have anything else to any other of those circuits you were showing me earlier?
Oh, I was going to say, this is the one I was looking for. It was right under my nose. And I couldn't, it was right there, but I've got stuff so all over the desk right now, so I couldn't see it. But
right.
this is one of the AliExpress, these are really designed to be phone chargers, but this thing will put out 8 amps at 5 volts. So this is, and it'll take 8 to 36 volts input. So this is what the LED sign here is actually running off of one of these, and a row of lithium cells I welded together in a battery with a BMS.
We take 8 amps for granted now. That little circuit you were just holding up, in the old days, I mean, my Lambda here, this thing is between 5 and 10 amps in it, and it weighs 30 to 40 pounds.
It's crazy. Yeah.
Yeah.
But that's an offline, precision regulated supply, of course. And this here is a switching regulator, which is why it's very compact. You can see the regulation control chips. And the other thing that actually I was impressed with the quality of this, it's got a conformal coating on it, a silicone-based conformal coating on it. So it seems like it's pretty rugged. I pulled the heatsink off just to get a look underneath. These are the switching FETs.
Right.
In that the smaller version of a D-Pack. I think they're TO252s is what that package is.
Right.
And the inductor is what we call bifilar winding. So that this toroidal inductor has 2 parallel windings wound and soldered together, and that's to reduce losses at high frequencies because of the skin effect. The current only flows in the surface of the copper at the higher switching harmonics, and so to improve efficiency and for lower losses in your inductor, you have multiple small wires instead of one big thick wire. So
now I thought that, here, let me see if I can show a bifilar. So I always pronounced it bifilar because we did know how to pronounce it back in the 70s.
that's how I call it bifilar too. Yeah, or trifilar,
or bifilar.
I say bifilar, but once you go beyond 3, it's now Litz wire. Because what are you going to say, quadfilar? You could say that.
So there's a bifilar winding, and to me, the total inductance is near 0. Am I wrong in that?
That's a wire wound resistor, though. So for high power resistors that use nickel chromium wire wound around a ceramic core,
right? But you can make a choke like this if
there's a lot of inductance. Each turn has to be separate for the resistance, otherwise they're shorting out, right? So they're insulated, but they're wound around a core, and that makes an inductor. So you don't want an inductive resistor, you want a resistive resistor.
Right.
So they wind them that way to have the inductance cancel out. You still get quite a bit of inductance, but it's a lot less than it would be otherwise.
But you can wrap
of a coil, you still have inductance. You're just using parallel wires to reduce the skin effect.
Okay.
Yeah.
Okay. And so where I see bifilar a lot is in toroidal coupling coils, and
Yeah.
that's like what's on your. Let me see if I can show a. I've got so many screens open here. I'm going to. Screen captures. There's one. So, very cool. Very cool. Well, we got about 4 minutes left to go. Anything you'd like to chat about during those 4 minutes?
Well, I think we pretty much exhausted the power supply topic. I just wanted to reiterate, when Bill, do you use a switching regular
Good
circuit or
question.
switching power supply? And the other thing I just wanted to point out, I love how you've used jumpers, rows of jumpers, to set the voltage for each of those outputs. I would want to go one step further and make little boards that plug into the jumpers that have, you know, a small CPU
like,
or MPU to and a display. Like, it's not a great leap to turn the board you're showing there into a nice, you know, digitally controlled.
Right.
You
could use little switches in there.
Use
Yeah.
MOSFETs or 4066 devices probably to short out the correct jumpers. And you could even get more different power supply outputs by having multiple shorts in there to adjust the resistor ladder, right?
As long as the switch did not change its resistance based on the voltage across it.
Right. Yeah, they're just equivalent to MOSFETs.
Yeah. Because if you look at some of the silicon controlled switches, and we used to do things like make sure they switched to ground and had the same amount of current through them and whatnot. Just because they can be nonlinear. A resistor is linear. The voltage across it is directly related to the current. But if you end up switching with some devices, it'll have a different RD on at 5 volts than it will at 4.5 volts.
Yeah, that's right. The resistance actually can increase over and different currents, of course, too. Yeah, it's not exactly perfectly linear. Hey, a question just came through as well on their Discord, asking about us weighing in on Bogatin's myth of the 3 capacitor values. But I don't know if we've got 2 minutes left, but I think we should dive into that perhaps next week.
And what was the question? I missed it.
Can we weigh in on Bogatin's myth of 3 capacitor values? This is something I've heard Eric Bogatin speak about at a conference in the past.
You mean don't just use 0.1, 1 microfarad, 0.1, 0.01.
Yeah,
right.
1.1, 0.01 for decoupling, and how that can actually cause problems in some circuits, in a lot of circuits, actually.
And actually, we did a show about that. I showed a spreadsheet that I gotten from Altera, and it showed how the anti-resonant points, you could accidentally line them up in the wrong place. I tend to use 0.47 nowadays, ever since I ran the spreadsheets for, a bunch a while back. And I just happen to like 0.47 now as a decoupling cap, and 0.047. So we're still a decade off, but those anti-resonance points just happen to line up a little better for me. Your mileage may vary.
We should dive into that, and we could maybe use Excel or use a spreadsheet, or you can even do this using a SPICE simulator. If you download modern SPICE models from AVX or Murata or one of the capacitor manufacturers, they provide accurate SPICE models now for the caps. That it's not just a dumb capacitor model. It's actually, they take that cap and they do measure a lot of samples of that value from that family, and they build a fairly accurate model that represents lead inductance, equivalent series resistance, and all of that stuff.
Leakage resistance,
it's all included in some of those models. And what we can do is plug those models into SPICE and look at the frequency response or reactance of the cap as it really would be. And if you put them in parallel in those decade values, yes, some very interesting things can emerge. And it really
So
is a dumb rule of thumb that's been superseded by science.
right.
So
And
Bogus
Chris
is
is
right.
asking if we could do high voltage supplies next or at some point.
I do want to do that. One of my bits of test equipment I did get off eBay that haven't had a chance to break out is a high pot tester.
High pot tester?
We're going to do that live one of these days. So I wanted to measure the quality of isolation of some low-cost LED power supplies from China.
Wow.
I believe they're okay, but they don't have creepage clearances on the board like you would expect for, say, a UL certified power supply.
Right. I can just see it. You go to fire off your high pot test, and just your picture just drops to a single dot on the screen. You know.
But that high pot tester is essentially exactly what is a 3,000 volt power supply. So.
Right. Well. Yeah. I'll throw out an old term here right as we're closing up. Remember TV sets when you turned them off and the sweep would stop, but the high voltage would still be there and you'd get a dot in the middle of your screen. Did you ever hear a name for that?
No, I never knew what that was called.
It's called a sniglet.
A sniglet? Is that official?
That is, yes, sniglet.
I love that.
There was a comedian that used to...
waving my hand in front of the CRT and feeling the crackle on my fingers, basically discharging it all into my body at the end.
Which as a kid, and I learned I could magnify, or I could magnetize the screen, the shadow mask in my CRT. My dad had to go, son, stop it, and that's how I learned to use a degaussing coil. He brought one from work. My dad used to work at a picture tube plant, which are probably not many of those left in the world, but that's, he worked for RCA in the 70s, making picture tubes.
Yeah.
So, well, excellent. Cool. Well, hey, my friend, good talking with you. Good. I think this summed up some bench supplies pretty good, and you did a great job talking about switching supplies in general. That was excellent.
Oh, we just hardly scratched the surface too.
And hardly scratched the surface. Yeah, matter of fact, I'd shown that big book I had on switching power supply design a while back. It just goes to show what I don't know is, inches of book these days.
There's so much. There's also zero voltage switching, zero current switching, resonant, semi-resonant, CPIC. There's so many topologies and ways of doing things to increase efficiency. It's really ridiculous how the industry has spent the last 20 years going from 80% efficient to 96.
Right.
That's where we're at now. 96% efficient, full load. Of course, you still lose power in all sorts of other areas in the design, but the power supply, they've really dialed it in.
Right. So.
Yeah.
Excellent. So, well, everybody, just a reminder, Coriolis-effect.com is, now I haven't posted late, the website's being moved, so I don't have the most recent videos up there, but there is the Discord invite there. And I guess we'll see you next week, my friend.
Yeah, it'll be good. Catch you then.
All right. Goodbye,
Enjoy
everybody.
your weekend. Bye.